In this video, we're going to attempt to calculate the electric field in all regions of an infinite coaxial cable using Gauss's law. Our coaxial cable has a non-uniform charge density of 2r, and we have an inner cylinder of radius a enclosed by an outer conductor, radius b to c. So to first start off this problem, we want to use this equation. EA is equal to Q total over epsilon naught. All right, our Q total is going to equal to the integration of our charge density multiplied by the derivative of the volume of the object that we're observing over epsilon naught. So if we want to find the amount of enclosed charges in r less than a, then we would denote it as such. So for r less than a, we can say EA is equal to the integral from 0 to r, charge density, P dV over epsilon naught. So what we do is we look at the area. The area here is going to be 2 pi RL. This is just the area of a cylinder. And we're using a cylinder for this problem because it's a coaxial cable. So we can just assume that it's infinitely long, and that would be the area of just the cylinder itself. All right, so we substitute 2 pi RL for A. We substitute the charge density for 2r, and we substitute dV for 2 pi RL dr. And the reason why we're getting 2 pi RL here is because the volume of a cylinder is going to be pi r squared times L. And what we get is we get E times 2 pi r L is equal to the integral from 0 to r times 2r times 2 pi RL dr. And we're integrating with respect to r here because our charge density is respect to r as well. And all of this is over epsilon naught. So what we get is we get E 2 pi RL is equal to, we can move our pi, it can move our L, and we can move our epsilon to the front. So we get, we can also move our 2's as well to the front. So we get 4 pi L over epsilon naught multiplied by the integral from 0 to r squared dr. And we just find this integral. So that gives us, if we just move over here, this integral is r to the third over 3 minus 0 to the third over 3. This just becomes 0. So then we just have r to the third. Let me just erase some of this up here. So then we get E 2 pi RL is equal to 4 pi L r cubed over 3 epsilon naught. So that would be our electric field for r less than a. And for r less than a, it's the charges enclosed by the cylinder for all the values less than a. And now we're going to want to find our next value for our electric field. All right, let me just clear some space here. We want to find for A less than R less than B. So when we are looking for A less than R less than B, we're looking for the charges that are inside A. We're also looking at the surface, the Gaussian surface charges as well. So we're actually looking for these charges or this electric field. So we do our same exact setup where we have E times 2 pi RL is equal to 4 pi L over epsilon naught times the integral from 0 to A R squared dr. And then we just do the integral as we did earlier. So then we get R over 3 minus 0 over 3. This just becomes 0. All right. And then this is from 0 to A. So our R becomes A. So we can do E 2 pi RL is equal to 4 pi L A cubed over 3 epsilon naught. And then we just divide our 2 pi RL to the other side. So we get E is equal to 2A cubed over 3 epsilon naught R hat, unit vector. And the reason why we're using R hat here is because our charge density is respect to R. So our electric field will be with respect to R as well. So let me move this over here. So this would be for A less than R less than B. And I didn't solve for this first one up here. So let me just math that out really quick. Let me divide by 2 pi RL. And we get the electric field is equal to 2R squared over 3 epsilon naught R hat. And the reason why these things cancel is because, we cancel out an R, cancel out a pi, cancel out an L, and then cancel out a 2. So that's how we're getting our answer. So this is our answer for R less than A. This is our answer for A less than R less than B. All right. Now we want to consider this region here, which is in between B and C. And one of the properties of electric fields and electric charges is that an electrostatic charge on a conductor doesn't have any charges. It can't contain any charges. So if you have a conductor, we can say that the electrostatic is equal to 0. Without applying an external power source, there's no electric field inside of a conductor, and there's none on the outside, simply because this is being grounded like this. So our final answer for B less than R less than C, our E field would equal to 0. And that's because this is inside a conductor. And then for R greater than C, our E field is also 0. And this is because it's shielded or grounded. So if it's shielded or grounded, the electric field would equal 0. And if we're observing a space between B and C for R, which is inside a conductor, then the electrostatic would also be 0, which would create electric field of 0.